Right, so thank you for joining and also attending your teammates' final projects. So this is, I think it's quite exciting course because it's the end where we put together knowledge that you are gaining since the beginning of this graduation. And your colleagues had the opportunity to work on 2 different projects. And I really love the way you took this challenge because the way it played out was, it's an open project, so you get to pick what you want to do. And first, they did an individual project, but where they took most of their time on exploration phase. So that was the first, what we call the POC, proof of concept, that we did in the beginning. And now as the second project that you are about to see, it was again an open project, but they took this opportunity to invest more time in the modeling phase. So of course they had to do the cleaning, but you need to manage your time, right? So it was quite nice that we managed to take this project phase and you need to make choices, and you will see ahead in time that in the perfect world, you would like to make everything perfect, right? So you go through the data science life cycle and all the boxes are like, you're really 100% comfortable. But the fact is that you don't have time for that. And this is something that we did see here in the project. It's only 1 month. It flies by really fast. And it's quite demanding. So, and having this said, we have 2 project presentations today. They are 2 groups of 2 girls each. So who wants to go first? Nay, I imagine you raising your hand right now. I'm not seeing you, but I see you now.
No, I did not raise this time.
I was
just
not
allowed to raise this time. No, not allowed this time.
All right. Who wants to go first?
Okay, we'll go first then.
All right. Okay. Katrina, did you give them permission to present?
I did not. Give me 1 sec.
I can't, maybe Maria can?
Yes.
I will try.
Okay, Maria, you're host actually right now. You have all the power.
So, sorry. Okay. Good. So here you can start.
Okay, so hi everyone. The project we're going to present today is about generating predictive analysis to detect financial frauds. And this is us, Maria and I. We've been working together for the last 2 weeks. Well, about this project, we only had 1 week because another week we are spending on deciding what to do. But yeah, the hands-on part we've been working on together for the last 1 week. And let me explain briefly first about our data. So we downloaded this data from Kaggle website directly. It's about a financial log of mobile money transactions. Actually, it's not a real original financial log because it's really hard to find this kind of data on internet available for public due to security and privacy issues. So the people who uploaded this data just simulated and synthesized this data based on real data. And yeah, so the problem, the tasks we want to address, to which we want to address a solution here, is that this data contains a column marking, stating if this transaction was a fraud or not. And also there is another column which is flagging if it was detected as a fraud or not by their system. And this flagging system works very poorly. So naturally, we want to build our own machine learning models, a predictive system to detect fraudulent operations better. So the workflow of this project was to collect the data first. And with this data, we did a little bit of exploration and analysis. And we transformed a little bit, just a little bit, so that we can feed these data to our models. And after feeding our data to this model, we generated predictions and evaluated our models using relevant metrics. I think from this part, Maria can explain.
So we decided for this type of issue we faced to use a classification prediction model, and I will explain you a little bit how it works. So for the classification model, we use what is called the conclusion matrix. What is made of is we have 4 squares: true positive, false positive, false negative, and true negatives. So the values we want to be high are the true positives and true negatives in this case. So the target in this project is it a fraud operation? That's what we want to know. And the features will be the relevant columns, as we will see later. We have different features that we, in the first cleaning part and transformation, we will look for. So here. This is what we call it first site analysis, because it's where after we import the data, or we visualize what the features are and what the given values are. So in this model, we have more than 6 million observations, which are the same as rows, and 11 features, which are the columns. In this case, we have no missing values, so that is really good, because sometimes you're facing missing values and you have to figure out how to work with them. And we have 8,219 fraudulent transactions between customer and customer. So what it means is that we have a column called type, and that column has different transactions: cash out, payment, cash in, transfer, and debit. And here we see that cash out and payment are the ones that are more frequently used. So these operations, some of them are fraudulent and some are not. So we look for which type of operation were more fraudulent. And we have customer to customer, customer to business, business to business, and business to customer. And the one that was having more fraudulent transactions were customers to customers. So in another hand, we have 2 features which are fraudulent and if it's tagged as fraudulent. So there's not many fraudulent cases, because we have 99% of transactions are okay, but these 0.1 cases are the ones to worry about. and the feature that is supposed to detect the fraudulent operation is not doing the work properly. So that's why we want to improve it. So we went for a heat map. In our case, the feature we want to focus on, although PV has the most important part of the project, is fraud feature. It is the one that tells you if it's a fraudulent operation or not. And as we see here, there's not many correlations. So the variable is fraud has not much relation with the other variables. So that is quite not good. So we can say we have a low linear correlation with the target. And other data that we saw at first sight was the amount of transactions, like the money that were on transactions. If they were valid transactions, most of them were lower than 200,000 in currency that we searched. The type of transaction, the fraudulent transactions were transfer and cash out. So for example, payments were valid. We didn't find any fraudulent payment. Operation time, fraud always is generally active over the month, and not fraudulent transactions are less active after the first 2 weeks. As I explained before, the recipient's type of transactions, C2C, are the fraudulent, and C2B, no fraudulent operations. As modeling, we decided to go for 4 different types of data analysis models. The first one is the logistic regression. Well, here did logistic regression and neural network, and I did random forest and XGBoost. Logistic regression is a kind of statistical model. Neural network is a machine learning algorithms that work as similar to the brain. You will see later. And random forest is a little bit more complex. It's a supervised, it's a bit more easy, but it is a supervised model that works with algorithms also. And XGBoost uses clustering, so, and it's an implementation of gradients, just to know. The metrics to make a conclusion, we thought that the important metrics to evaluate were the conversion metrics, is the table that I showed previously, the area under the curve. We will see that a curve represents the rate, and when the area of that curve is bigger, is because we have the recall and the precision high, which are really good parameters to consider that our model is really good. And the recall rate is the rate that predicts the correctly. So is what it does is a recall rate is takes the true positive and true negative rates, and we give the result. If it's close to 1, means that the recall rate is really good and the model also is good. You?
The first machine learning model that we implemented was logistic regression, because it's the most common and simple approach used to predict the binary class. And as a first step, we built a baseline model without changing any hyperparameters, just a simple basic logistic regression. And if you look at the confusion metrics, the true negative rate converges to 1, so it's 100%. It means when it's not a fraud, it almost perfectly detects that it's not a fraud, but the true positive is only 0.44. It means among the all fraudulent operations, it can only detect 44% right. To correct this, we added class weight hyperparameter to this function. By adding this hyperparameter, we are forcing this model to learn that there is an imbalance in this model and it will adapt it. And the result of the improved model is like this. So as you can see, the true positive rate has increased a lot. It's almost 99% correct, but then the false positive rate has increased a little bit. So as a trade-off, we got a little bit more of false positive rate, but we get more false positives than before. And from the same baseline and improved logistic regression model, we plot the precision and recall of each model, and the first recall score, which is the proportion of true positives. So recall means when the system flags an action as a fraud, and when it was a real fraud, it's a recall score, and in the baseline it was only 0.438, and after adding the class weights, it improved to 0.986. The second model algorithm of the super learning model we implemented is neural network. And here I selected sequential model from Keras because it's very simple to construct. You only need to specify how many layers you want to activate and how many nodes, neurons each layer will have, and how many epochs you want to give so that the model can repeatedly learn about the data. And I brought two examples. In the trial one, the first purple graph is the loss of the model. So it's over the 8 different learnings, the rate of error of our model is presented as a loss. And the bottom, the recall, is the orange graph. So like before, we are interested in increase the recall to remove the false negatives and increase the rate of true positives. But in the trial one, the loss and recall is a bit random. There's no distinctive trend. What we are interested in is to reduce the loss so that we can reduce the error of our model and increase the recall, like we see in the trial 2. So in trial 2, there's a tendency that loss is becoming smaller and recall is increasing. And I expect this to be better by increasing, by modifying the number of layers and the epochs and neuron numbers. So, but those kind of optimizations are still left to be done for the future.
So in my case, in the XGBoost model, I got really a high rate of true positive and false negatives, which is what we were looking for, really for a good model. And as you can appreciate from the curve, we have a big area. That's what I said before. If we have a big area, is because the recall is high, and also the precision of the model is high also. So the recall score in my case was 0.78, which is lower than what he got in the logistic regression model, but I got a better precision rate. So at the end, our model ends up by having this look, logistic regression in the recall scores order goes first as a better model, and XGBoost, neural network, and random forest go for the last one. And for the final statement, we detected fraudulent detection with high precision and high recalls. By building different kinds of model, we were able to find the most satisfying model because of the recall, the precision, and also the processing of the data, which is also important when we are dealing with so much high data. And for the future, we want to optimize the models and predict other more complicated data. So thank you for listening, and if you have any questions, we will be glad to listen to them.
All right. Congratulations, first of all. Before I give my comments, I'll do the same as before, but I just want to add everything with the whole class was attending. There was an additional challenge for the second phase of the project, and I think it's relevant, and Hugh mentioned in the beginning. So when you have an open project, one of the challenges is you want to do a lot of different things, right? You learn a lot, but the problem is not all the data has what it needs for us to go further. What I mean by this is many times we hit a wall because the data quality within that data does not allow us to go any further. And because of that, in the beginning, the whole class was thinking on doing the whole work together, and we did lose 1 week. And I think that's also a relevant point, because maybe in the future, I would suggest not to be so open, but then that's something we need to think about, because it's also good to give you freedom, but it has this downside of the coin. So having that said, before I give my comments, I want to ask the class and also our guests to, and future colleagues, right? Because you're already doing the course, to ask any questions or comments. Doesn't need to be any doubts, but comments to the work from your colleagues on what they did, how they did. Was there anything that you would like to take learnings from them? Because maybe in the future, you would like to also to do a fraud detection model.
Okay. First, big congratulations to you two. I'm super proud of you. I feel emotional, actually. How much fear and doubt along the way, especially around project phase, and if you'll be able to do this in such a short amount of time. And I'm pleased to say that you've proved yourself that yes, you can do it. Certainly you're exhausted, but really thorough work done here. Great job in starting with the problem and talking about where you got the data, what metrics you would use to evaluate, and next steps, right? Just so a quick question. Well, first, I'm sort of curious to know what the logic was in pursuing this particular problem, one, and two, this is, so you use different data, Hugh, than last time. In your individual project, you were working with text data, and now you were working with financial data. So I'm curious to hear what that was like for you, if there were different challenges, etc.
Here, you first.
Okay, so about different types of data. For the individual data, individual project, I chose language text data because that was the topic I that I felt the most insecure about. So I wanted to practice and improve. And about this data, the table with numbers, I was more comfortable. I like more this kind of data. So yeah. And before it was more about data cleaning, but this time it's about prediction and modeling. So I feel very, I don't know, I feel very proud to be able to do, yeah, different tasks into projects.
Excellent.
And well, about the logic of choosing this data was, well, we looked at, like, I don't know how many data sets we looked at, right, Maria?
Not just the data, but the problem of wanting to build a fraud detection model, which is really commonly used, right? We had this at eDreams. It was their first data science department.
I think it was interesting because we could apply different modeling types. So it was nice because of that, and we could discuss which one was better and how to clean the data and everything. So I liked it more than the individual to do it with a partner. Yes. I think they got scared.
I want to ask about the neural network. How did you come up with your first architecture of the neural network? How many layers? How did you decide those parameters?
So I Googled at first how to decide these numbers, and they say it's heuristic. So it means maybe practical, empirical. You have to try and set change the variables. So since we had 10 features, I think, I just played around that number, 16, 24, 8. Yeah, I didn't go too higher because my laptop cannot handle those.
Any more questions? All right. So again, getting back to the point that Katrina was saying, I really like to congratulate you for the work that you did here. It's quite different from what you did before. And we did have, the hip up of when to start and so on. The other thing that I find here is something that I've discussed in our, let's say, not 101, 2-1, right? Which is, this is a common problem in terms that you see a lot in the industry, trying to find what you have, which is an unbalanced problem. And I'm not sure if you all noticed that when your colleagues were showing the confusion matrix, what happens in these sort of problems is that, well, you have a class that it's so well represented that your model is not really that bad, but it's missing what we really want. So we tend to have a false negative rate quite high. And one of the important points during this project was to identify two things. Which models do they work better for the problem? Because that's a really important point, but also which metrics should we look at, right? So I think, and my advice for you, if this was something that you would do in the industry, you should pull that in your presentation. You should raise that, well, please do notice, why am I picking this model? Because perhaps the metrics that you're looking at, they are not really the best ones, but they are because the recall is higher. Because in your case, you want to recall higher because it's where you can actually capture the highest number of fraud cases. And that's why it's so challenging, right? I think that's another really great point and I do know that it was quite challenging for you. The other one is something that we actually face all the time, which is even when you are because, you know, we talk a lot about cloud-based clusters and so on, but the fact is that it's quite hard for us to take advantage even of those. If you would implement your solution in a distribution manner, it takes time to do that. So what you both of you did, and I'm not sure if I missed it, Maria and Hugh, but please tell me if I did, because you did downsampling. So you could test the model if it worked well, and only when you are comfortable, you put it running for everything, right? So this is something that you did. Do you want to tell a bit to your colleagues why you did that and how you took advantage of that technique? I mean, one of you or both of you?
So you mean we tried undersampling first to try the model? Because our data was huge. It has more than 6 million entries. So to run a model once, it took several seconds or several minutes. And to optimize the performance of the model, we have to change the hyperparameters and so on. But it took so many times. So we tried with the small number of the samples first to assess the performance. And then we tried with the entire data set.
Exactly. And that's a quite important strategy, right? Because it allows you to get comfortable with the data, because the trick here is get a sample that is representative of your data. You are comfortable, this is the model you want to go for, and then you actually leave it running. And one of the conversations we had is, then when you are there, leave it running, go for the report, right? Another thing that I really want to, this is more a comment again, I think it was quite nice to see how you, on your own, because this was not with my influence, I asked you to do it, but you did it all by yourselves, was your capability to split the work by the two of you. And I think that's not an easy thing to do. So what they did was the exploration in the beginning. They took the time because you need to know the data, but then they got together and decided, I'll go for this family of algorithms, and then I go for another one. Because if you notice, both Maria and Hugh, they chose two different family of algorithms, right? So this is how they split their work. And I think this is also something that it's quite valuable, because then they also managed to put it together again. And finally, regarding the collaborative work as a team player, they also put the project report on, I think it was Google Drive, right? And both of them were putting things together in there and then just building on top of that. And here it worked really well, and I'm really happy for you, but it's not an easy thing to do. So that's the thing. It does takes a lot of exercise to work well with people who have different work, I don't know, techniques. I don't know. We have, all of us have our habits, but when we are working together, we need to manage to put it, you know, well, very well, because you have a deadline, and that's it was quite nice to see. Yes, I think those are my comments, and I'm looking forward to look at your report. And what I'm going to do is, and this will be for both groups, I'll go through it, I'll add comments, and I'll just send out by Slack a final, because there's one, again, for everyone. The advantage of the report is that you have room to explain better without being on, let's say, like what we're doing right now, on writing what you did, why, and so on. And that's also something that we need to do many times. And I'm going to give you feedback on that line, which I haven't done so far. Okay, all right. Then again, congrats. And Bruna, Inea, if you want, you can go for it. I think, Katrina, you need to give them authorization, I think, for them to be able to present.
Actually, Maria, can you, because you are the host at the moment.
Who presents, Bruna or Nia?
You can give it to Niha. Niha is starting, I think.
Yeah. Bruna, you are the host now.
So I guess I'm starting. No, Niha, you have to be the host. How can I don't know how to do it.
Transfer your hostness to me.
I have no idea how to do this.
In the
You
security,
click
there
on
will be.
participants.
What participants?
Yeah,
Yes,
so
and then
go to the share screen.
Oh,
There's
what is this one? MFA helping me. Okay.
So go to shared screen.
I can go to participants and then where is Niha? More and then make host.
just to
Perfect.
be able to share.
Perfect.
Yeah.
Not that hard, huh?
Got it.
Command line is easier for me all the time. This click stuff I don't like.
Okay. Can you see my screen? I cannot see anyone. Can you see my screen?
Yes.
I
Okay.
can see, although it's not in present mode. Perfect.
Now, okay. Hello, everyone. My name is Neha. Me and my project partner, Bruna, we are going to present our CodeOp's final project. That project we selected is Spotify's modeling song features. In this project, we are working on two objectives. One is we are building a classifier, and one we are building a recommendation engine. So first, we will see how this document is outlined. So step by step, we will go. First, we will start with the objectives. We will define what our objectives are. And in the second part, we will fetch our data to fulfill our objectives. In the third part, we will explore our data for the analysis to see the feature importance, to feed this data into the modeling. Here we are using different classification models for the classifier, and then there is one recommendation model. And we're gonna wrap up our document with the conclusion and the future steps. So we will start with I will start with the objective. In this section, we are going to see we have chosen two objectives. The first objective is the classifier, building a classifier. In this objective, we are using different machine learning algorithms to build a classifier for our given data and predict whether a user will like a song or not. Here, classification is a supervised learning concept, which basically categorizes a set of data into classes. And the two classes we are using here is the songs we liked and the songs we do not like. And the second objective is building a content-based recommendation system. So here we have our own personal data from the Spotify, me and Bruna. So we are going to build a recommendation system based on our song features to see the similarities of the songs. Now, to fulfill these objectives, we need data, and we fetch our data from the Spotify's web API. And in this section, I'm going to explain how we fetch our data from the Spotify web API and the authentication process. So if you are not aware about what Spotify is, I'll give you a brief introduction. So Spotify is a digital music podcast and video streaming service. It launched in October 2008. And in terms of data, it has over 60 million songs, that is around 200 petabytes of data. And it has many parameters for the user interfaces. You can search the songs based on artists, albums, genres. You can create your playlist, and you can add it, and you can share your playlist. With the New York Stock Exchange I think in October 2017 or 18, I'm not sure. it was stated that Spotify has 299 million monthly active users plus 138 million paying subscribers. So the reason behind these many users and subscribers is its personalized recommendations. The way Spotify gives the personal recommendations to its each and every user with the discover new music, the discover weekly playlists, it's making it going high on the peaks, you know. So that's the introduction about our domain on which we are working. Now how we got our data from the Spotify. So Spotify allow users to access their data from their developers platform and the web API. To access user related data through web API, we need an application authorized by users or the app itself. So the authorization process involves three parties. First is the server, that is our Spotify server. Second is the client, that is the application we are going to authorize. And third is the resources. Resources is our data which we want to collect. And to obtain these authorization, we need to go through the three steps. First, we have to go and set up our developer's account. Second, we have to register our application. And third, we have to use the authorization flow. Okay, so this is my Spotify for developers page from where you can make your account. If you go here on the dashboard and you log in or sign up with the account, here is an option that is called create an app. Create an app is going to be our client. So I click on this and I put an application name and a description, and I agree with the terms and conditions. So I got this data, I got this application. Similarly, Bruna did the same. And with this application, when we click on it, we get our client ID and client secret, which is we're gonna use in our authorization flow. Back to the presentation. Now here we are using the client ID and client secrets, which comes under the client credential flow. So the client credential flow is a server to server authentication. So in this, we do login with our client ID and secret, and we get the access token. So this is the workflow, how client credential flow works. So here with our application, that is our client, we are requesting for the token with our ID and secret to the server, Spotify server. It's giving us the access token. We are requesting with this access token to the web API in the Spotify web API, and we are getting our unscoped data in the JSON format. So this is how we are processing to get our data, to fetch our data. So now that was a bit theoretical part, how we did implemented in our practical part. So we use the Spotify library for the Spotify web API. It's a Python library. It provides the full access to all of the Spotify music data. All we need is the credentials for our data in the Spotify. For example, our playlist IDs or URIs, song IDs and the URIs, and our client ID and secrets. So in this Spotify library, we are importing it. We are using the .util method and the .oauth2 method to authorize. So util gives us the playlist, but to get the playlist, we need to authorize it. And so the OAuth2 is basically the practical version of client credential flow. So this is how we implemented it. Here we are giving our client IDs and secret, getting the tokens with the get access token, and we are authorizing it. So what kind of playlist we are using? So for me, I have on my Spotify, I have 600 songs that I like, 400 songs I don't like, and there are 60 songs we are using to validate our models. So the first, these 1,000 songs we will be using to model, to check our models, to train our models, okay? And the last 60 song validation set we will be using to validate our models. in Bruna's case, we have around 1,300 songs she likes and don't like, and 100 songs for the validation set. Our data sets are not big in size, but we created in like 1 or 2 days sprint, so it's enough. Okay, so now we have our data, we fetched it. Now we have to do some exploratory data analysis to gain some insight how our data looks like, and to see what features are important for our model part, and to see how the correlations between the features works. So basically we are doing this part to gain insight from our data. So this is one data frame, one data set from Bruna. It has around 1,300 rows with 13 song features and 5 features in the in the string which represent the IDs and the links. The main features we will be focusing on will be these song features, the audio features, which are, out of which 10 are the continuous ones and 3 are the categorical ones. Out of this, we created one of our target value where we are doing, which contains our class labels, which is like and not like. 1 represent the songs we like, and 0 represent the songs we do not like. So now we are going to see some visualization one by one for all our features. So first we will visualize how our target looked like. So as I told you before, our target has the class labels likes and not does not like. If you can see here in my data, I have around 600 songs which I like and 400 which I do not like, and it's highly unbalanced. And similarly in the Bruna, she has around 1,000 songs she likes, and around 200 or 250 she doesn't like. So this visualization is very you can say informative for us to see, or to understand at the end in model what kind of evaluation metrics we're gonna use, because our data is highly unbalanced. Now for the other features, for example, the danceability, we are going to use the Seaborn's violin plot. Seaborn is the library for statistical graphics, and the violin plot is the combination of box plots and the kernel density estimation. Here in the sorry. Okay, so in the violin plot, it gives us the inside information. For example, this white dot here, it gives us the median value. The above part of this box, it gives us the 75 percentile of the data, and this part gives us the 25 percentile. And these were I don't know what to say, whisk, I guess. These upper and lower wicks contains the 25%, remaining 25%. And this part here, the amplitude, the width of this leaf it gives us the distribution, how our data is distributed. With the violin plot, we also calculated Mann-Whitney test to see the significance of our distribution, if they are different for the categories, they are different or not. So for example, for the danceability is the danceability feature represent it's from the range 0 to 1, and it gives us information about the music elements, if the of a track, if it's the song is danceable or not, with the high tempo or rhythm stability, beat strength, or overall regularity. As you can see in the distribution here, we have the p-value is very far from 0. Sorry, I forgot to tell you the threshold for the Mann-Whitney test. We are using the 0.05 to see if it's greater than 0.05, the p-value, it means it's not significant, while if it's less than, it's significant. So we are considering the distribution which are the p-values which are less than 0.05. Similarly, we drew the violin plot for the energy. It ranges from 0 to 1. It represents the intensity and the activity, and the energetic tracks feels fast and lousy. And it also gives us the information about the medium, the 75 percentile, the 25 percentile of our data, and the distribution, how it's distributed with the p-values from the Mann-Whitney test. I'm not going to explain every features here, because we have around 13 features. So I'm just going to explain what features we have. So for example, loudness is in the decibels. It ranges from -60 to 0. Loudness of a track in decibels actually explains the strength, the amplitude of a track. Similarly, the speechness, it ranges from 0 to 1. It detects the presence of spoken words in a track, if it has a lyrics or not. And the acousticness is a confidence measure of whether the track is acoustic. One represent high confidence and the track is acoustic, and the vice versa. The instrumentalness is, as you can say, the opposite of speechiness. It has the instruments with no lyrics or little bit lyrics. So it ranges from 0 to 1. So higher the values, higher the instrumentness is, and the lower the values it's more speechness. So we with the description we can see some of the features has the similarities here. Liveness, it ranges from 0 to 1, and liveness is it detects if the song is played live in front of audience, or it's recorded. Usually the songs are. The valence describes the music positiveness conveyed by a track. Track with high valence sounds more positive. It gives the happy, cheerful vibes, and the low valence more the sad, depressed, or angry kind of vibes. The tempo of a track, it's a beats per minute, the BPM. It ranges from 0 to 210, and it actually tells us about the speed or the pace of the song with the average beat duration. Here with the test, we have the p values for me is the greater than 0.05, which is not significant, but for Bruna it is. And with my data is more mixed, and seeing the difference in each feature is quite confusing in my data, rather than comparing to Bruna's. And the duration is the time of a track in the milliseconds. Here also I have the p values greater than 0.05, not significant, while the Bruna has. Now we have the categorical feature, that is key. Key is it's a pitch standard pitch classes. So so it varies from 0 to 11. So in my case, as you can see, I have more liked songs on 0, and the more disliked songs on 1. While in Bruna, we have the more liked songs on 1, while on 0 key, sorry, and disliked songs, it's 6 or 7, in between the 6 or 7. And I don't know the key names, maybe C sharp or or something. For 0, it's a C. And for the mode represents the major minors of the track. 1 represent the major, and 0 represent the minor, and it's a bins distribution. Here we have for the dislike songs, we have the higher mode for me, and for the sorry, okay, it's a 0. Okay. So the darker color songs are the songs I liked, and the light color songs are songs I don't like. So it represents the so the 0 mode is represents if the songs are minor, and the 1 represents the songs are major. Okay. The time signature is a notational convention to specify how many beats are in each bar. So for both me and Bruna, we have maximum like songs on the 4, and same for the dislikes ones, and for Bruna also the same on the 4. Okay, so it was now up to now we just have seen what our features are and what they mean. Now we are going to see the feature correlation. Feature correlation is a way to understand the relationship between multiple variables and attributes in our data set. So using correlation, we can get inside information such as one or more attributes depend on another attribute, or cause it can be a cause for another attribute, or it can help to predict one attribute from another. If we have the missing values, then that's the best way to see the correlation and discard those missing values with the appropriate values. So here, as you can see, we are using the heat map correlation, and the darker the color, higher the correlation is, and the lighter the color, lower the correlation is. The range of the correlation is from -1 to 1. So the -1 is the perfect inverse correlation, and 1 is the perfect positive correlation. The positive correlation means if if a feature is increasing, and if two features has the positive correlation, that means one feature is increasing, then the second feature is also increasing. It has a linear relationship. As we can see here, 0.7 for the loudness and the energy. So this is the highest value we have for the correlation. So we can see the energy and loudness, they are highly correlated. While if we see for the energy and acousticness, we have -0.73. So it's a negative correlation, and it says if energy is increasing, then the acousticness is decreasing. So it's an inverse correlation here. So out of this heat map, we took the two most highly correlated pairs of features to see how they look like. So for the highly positive correlated, we have loudness and energy. When we see the scatter plots, we can see that they are linearly, they have the linear relationship. If energy increasing, loudness is also increasing with it, and it has a positive correlation. And the Pearson's R is 0.74, because Pearson's correlation is for the linear for the continuous variables who has the linear relationships. And the feature correlation for the inverse correlation value, we have energy and acousticness with the 0.73 value, and we can see it is highly correlated with in the inverse way. That means if acousticness is increasing, the energy is decreasing. Okay, so we have seen the correlation up to now, and we have seen with what features have the correlation, and with that with this help we can do some feature engineering, which we haven't done now, but we are thinking to do it in our future steps. Before moving to the modeling, we have seen some my and Bruna's average, like how average like song look like and how average dislike song look like. So for that part, for the like songs, we use the target value equals to 1, and for the dislike one, we use the target value equals to 0. So for each continuous feature, we are calculating mean and standard deviation, while for categorical one, we are calculating the mode for each feature. Then then we are filtering only the songs that have values between the average -1 and +1 standard deviation for continuous, and the equals to the mode value for the categorical. So this is how we calculated, and for me the average song look like from the Adele, that is Rumor Has It, and yeah, you can say that's the song I like. And for Bruna, it has Liking a Rolling Stone for Bob Dylan. Similarly, for me, the average song that I don't like, that is it's an Indian song from the same name, Neha Kakkar, and Ironically, for Bruna's average don't like song, it's a song from Brazil. So we both don't like the songs which are from our home countries. Okay, and after that we did a principal component analysis for our for our data. Principal component analysis, the PCA here we are using to see the linearity, it's used for the linearity dimensionality reduction. It's a technique for the dimensionality reduction technique, and it can be utilized for extracting the information from a higher dimension space by projecting it into the lower dimension subspace. So the dimension here I'm talking about are features. So as you can see from the graphs here, we can see in my data, my like songs and dislike songs, they are superimposing each other. So it's very hard to distinguish between them. So all the features are mixed. There is not a we cannot separate my liked and disliked songs easily. But while in Bruna's case, we can create a separation between the like songs and dislike songs. They are like different clusters here, and so we can easily distinguish that, yeah, in this part the songs Bruna does not like, and in this part Bruna likes. So with this part we finished our EDA and result with the what features are the important and what kind of evaluation metrics we're gonna use. Now the next part is the building classification model or the recommendation model. This part Bruna is gonna explain. So Bruna, you can take now.
You can keep going, I think. Just go next when I finish.
Okay.
It's fine. Then we don't waste time.
Okay.
So as Neha said, now after the exploration of the data, we started with the modeling part, and we had same approach as Hio and Maria. We tried different models. So we have two main parts. We have a classification and we have recommendations. So first we'll start talking about the classification models. So which models we test for the classification? We started with the logistic regression as a baseline, as the girls did. Then we tried decision tree, random forest, and XGBoost. And the logic was to go for the most simplest model to the most complex ones and to check which ones will give us better performances. So the following question is how to evaluate the models. So we also had to discuss about this. And we are looking at the three different ways of evaluating the models here. We have precision, we have a recall, and we have F1 score. So depending on the objective, depending on what you want to do, you should select a different metric to evaluate your model. In Spotify, they have different recommendation systems. For example, they have this discovery playlist that every week they give you a set of 30 songs to listen, and this is limited. You only get 30 songs. And for this, we think that precision should be more important because you want to get these 30 songs right. You don't want a bunch of songs. You want these 30 songs that you have right. So in this case, you want to reduce the false positive rates. So precision here will be the metric that you optimize in our point of view as users. Some other playlists from Spotify, they give you like unlimited playlists. If you scroll down, they keep giving you songs and more songs and more songs and more songs. So in this case, maybe recall is more important because you want to get everything that you can possibly get to recommend to that user. So in this case, you want to maximize you want to minimize the false negatives. And then in our case, we don't have a specific objective like this. So we decided to try to maximize the balance between the precision and recall. So we want to have a model that is precise and also has a good recall. We cannot maximize both things altogether, but with the F1 score, we can maximize the balance between the two metrics. So that's why you're trying to, in the models that we're testing, our metric at the end, the objective is to maximize the F1 score. And the F1 score, the highest the closest one, the highest is the precision and then the recall. If you have an F1 score of 1, you have 100% precision and 100% recall. So we started with, next Neha, please. We started with logistic regression as a baseline, as the girls did as well. So it basically describes the relationship between a dependent variable, which is binary in our case. So our target is like or dislike, 0 and 1, and a set of independent variables. In our case, it will be the song features. And the core thing of the logistic regression, it is the sigmoid function, which maps the output that have of your function between 0 and 1. It's called like a squashing activation function. So with this, in the classification task, usually what we do, if your value falls above 0.5, you select this as 1, and below you select this as 0. So for the first the baseline model, the logistic regression, this is the metrics that we get. We get precision for NIHA around 6.1 and 100% recall. And for me, precision is 0.8 and 0.96 recall. And when we look at the F-score, the measure that you want to maximize, for NIHA is around 0.74, and for me around 0.88. So this is our baseline, the most simple thing that we could do. We used all the features, the most simple model. And from this, we try to improve the F1 score. So the next model that we test was the decision tree. So decision tree is basically a flowchart-like tree structure, like this one that you see here in the picture. So you have a decision node, and each internal node represents a feature, and each branch of the tree will represent the decision rule. So for example, here I could have energy of the song. And then decision tree will say that above this limit of the energy, the song will be classified as I like or I don't like. And the tree keeps splitting in to get the leaf nodes, and on the leaf nodes, you represent the outcome. So each one of your observations, you will end up in one of these leaf nodes, which will give you the classification for your song in our case. And for this model, we get F1 scores of 0.75 for NIHA and 0.91 for me. So as you could see from here, my data set is way easier to classify. Even with the decision tree, I'm getting scores of F1 like around 91 already. And NIHA's, it's way lower than mine, because as you saw, NIHA's data is, I think NIHA is a more tricky user to predict what she likes, what she doesn't like, because the features of their songs are very overposed. Next one. So next one is a random forest. So forest is like a set of trees. So we will start with the tree, and then we build the forest based on the trees. So the random idea here, so it creates decision trees, selecting data randomly, select subsamples of your data and select sub features inside the feature data. And then it builds different trees. And at the end, you get a prediction from each of these trees. And then we'll select the class of your song by voting. So your song will be, you have any number of votings for each tree, and then you sum up these, and the one that has more votes, if you like or dislike, will be the final classification for your song. So this in theory is more robust than one single tree, but builds up on the second decision tree. And for here, for NIHA, the F1 score was around 0.8, and for me, around 0.93. After we show all the metrics together, then we can compare the models side by side. And the third model that we test was the XGBoost, the same things that Maria and Rio tested. So with XGBoost is considering actually the state of art in machine learning when you have structured data, you have exactly kind of data that we have. And because of speed and performance is super good in XGBoost, and the core algorithm is parallelizable, you also can run in graphical units if you have this kind of system available. It's super fast. And when you go to different machine learning competitions, it also overperforms on other algorithms. And another good and bad thing of XGBoost that you have a lot of parameters to do. So you can spend, I don't know, the rest of your life trying to turn parameters, and it's a very good thing. It's flexible, but also it's more like an art to turn the parameters. So XGBoost is extreme gradient boosting, and boosting is like a sequential technique. and which works on top of an ensemble. So the idea is to combine a set of weak learners, and in our case, the weak learners will be trees. So we are building up on trees. So in this case, instead of taking random samples of data and of features, the thing here is sequential. So we build a weak learner, a tree, and the next tree that you build sequentially will learn from the mistakes from the previous tree. So the prediction of the model is improving by learning from the mistakes of the previous models. So as we go, please, as we go, so when the predictions arise from the single tree, the outcomes that are correctly predicted, they are given lower weights, and the ones that are wrongly predicted are given higher weights. So in this way, I can learn from my mistakes and improve in the next iteration, okay? So the idea is to try to reduce the misclassification rate across the iterations that you have with the model. Next, please. So for XGBoost, we have for Niha the F1 score around 0.8, and for myself 94. And then we try the same model, but trying to do some hyperparameter optimization. So you can do it by hand, by yourself, trying different hyperparameters, but there are so many and so many combinations that you can test that this is not feasible at all. So it allows you to use this technique of random search of hyperparameter values. So basically build a grid of hyperparameters, things that you think that are important for your model. You choose a range of values, and then you iterate over this range of values, in this case randomly. So here we tried 100,000 iterations. They're setting up 10 different parameters, I think. So this helps to control overfitting of your data. So you can set different parameters. You can set a subselect, just a specific proportion of my data or my columns. You can cut the depth of your trees by, instead of using a tree that is super deep and will be the model will be super complex, you build up your model with trees that are more simple. Then you can control overfitting with this. And also you can improve the performance of the model, changing some kind of hyperparameters. And one parameter here that was really important for us was this scale pulse weight that deals specifically with the imbalance in the data. And as we have our target value is super imbalance, this allows us to control for that. So after we did our hyperparameter optimization, we got slightly better results. Can show Niha. Can put on the final table that shows everything together. So here we are comparing all the models that we test. So we started with logistic regression. I'm always looking at F1 score here in our case, but if you want to maximize another metric, you could try different models. So for us, the one that maximizes the F score is the XGBoost with the hyperparameter tuning, but the difference is not super high. Even the random forest here is performing very well, at least for Niha, the difference are not super high. For my case, I got better models, like every single model, even my logistic regression is better than the best model of Niha's data. And for me as well, the best model in terms of F1 score is the XGBoost with the hyperparameter tuning. But the difference, if I compare with and without hyperparameter tuning, are not super big. But it's the best model that we got for both cases. So then we had this idea to try to validate the predictions of our models, building up the validation data sets. And the validation data sets would be composed by songs that we don't know. So Niha selects 6 songs that she doesn't know. I select 100 songs that I don't know. And we manually classify it song by song. We listen to the songs and we put 1 if we like the song, 0 if we don't like the song. It's a bit of a pain, but at the end is fun to do. And then after the classification, we compare this with the predictions of our models to see if our models are predicting well if you like the song or if you don't like the song. And then we use the XGBoost with the hyperparameter tuning to check if this was good or not. So the F1 score was lower for me and for Niha as well. So here we got around 81 for Niha and around 85 for me, but it's a pretty decent score. And we had just, I don't know, super small data set, so it's hard to take a strong conclusion from this because we just had 60 songs and 100 songs, but it seems to be working. Some room for improvement, but seems to be working. Then the next step was to build a recommendation model. So for this, we used the merged data set. We merged my songs and Niha songs. In total, we had 200,460 songs in our final data set. And the idea here was to do a content-based recommendation. We used k-nearest neighbors and the Manhattan distance. We also had a discussion about which kind of distance to use here. Unfortunately, I didn't have much time to dig deep, so I just trust the state of the art that I found, that Manhattan distance is the metric that is preferable when you have high dimensional data. And another thing that is important here, before we do the measure of the distance between our songs, is to standardize the features, because our features have different ranges. So if you have a feature with a super high range, for example, this feature can dominate your distance. So the first thing you have to do is to standardize, put them all in the same scale, and then you can measure the distance. So by doing the k-nearest neighbors, we select the top 5 songs more similar to the query song that you want. So here we have a song from Frank Sinatra, and then we had 5 recommendations for a song of Frank Sinatra. We have 2 Frank Sinatra songs, which is cool because, okay, it works, gets things similar, but it's a bit boring. So imagine a model, well, if you like Frank Sinatra, just keep listening to Frank Sinatra and that's it. Which is cool here, that you get another things that you maybe not expect. And I was listening to the songs because I didn't know all the songs, and you get this kind of the vibe, the feeling of the songs is really similar. And these bands like are super new and the style is not exactly the same, but the vibe of the song is the same. So it's very cool to see that with the features, that's magic features that Spotify was able to define, you can get this kind of feeling that the song is similar to each other. It's very nice. Another example, Coldplay here, you also get songs from Coldplay as recommendations, and another kind of songs that also have the same feeling, the same vibe. And last example, so a song from Brazil. So to see that I don't hate songs from Brazil, this is a very good one. I just hate the bad ones. This is MPB from Gilberto Gil, is very good song. And you also have things similar like artists from Brazil, from Bossa Nova, and also some things that were unexpected to me. But when you listen to the songs, it really makes sense, the recommendations. So our conclusions and possible future steps. So for the classification part, so the performance of the model are very dependent on the user likes and not likes. So if you have a user that likes and dislikes more or less the same thing as Niha, it's harder to predict. It doesn't matter which model you use, this will be harder than a user like me that is more like, my likes are more dissimilar to my dislikes. And also the evaluation metric that we select to evaluate the models depends on the use case. If you want to get more precision, more recall, the balance between the two, this depends on the thing that you're trying the problem that you're trying to solve. And the correlation is the recommendation, sorry, it seems to be working well. We have Niha. So we have songs that are similar, expected, but we also have some sort of, I don't know, diversity in the recommendation. So it seems nice. And for future steps, what we have to try to add more songs. The more data we get, the better. That's for sure. And to do some feature engineering based on the correlations that we found. So try to create some sort of meta features, combining different features of the features that Spotify already has. So to see if you can improve the predictions of the model with different features. And also to do at the end a collaborative model of a recommendation, trying to merge our recommendation model with the classification model, and also adding different features of the songs. And here Spotify doesn't allow you to rate the song. You don't have this kind of rating, but you have the rank of the song. So we can try also to use this kind of feature and introduce these in the recommendation model as well. So the technologies that we used for this project of 1 week was the Spotify for developers, the API. We implemented everything on Python. We used GitHub to share the code between us, and also use the Jupyter notebooks. We also built a Docker image to run our notebooks, and like every single computer that you can imagine, we run the same thing and work and perfectly. And Google Drive to share the report and the presentation, and to be able to work together during this time, which was very, very helpful as well. And that's it. Thank you, and questions.